Hi, good morning, everyone.
Good morning, David.
Hello, when? Let's see, to share the slides. I started.
Hi, Young. I don't see him on yet.
Oh. I don't have his phone. Let's see.
I just sent him an email with the link again to hopefully he'll join here soon.
There is a story behind this. There was a famous academician, Butker, who was kind of one of the best in nuclear physics back in the former Soviet Union. And he would like to say a necessary condition for a seminar is the presence of a speaker. and hear it. And it's also important that the speaker doesn't fall asleep before the audience does.
I'm here. I'm sorry, I'm a little bit late.
Great. Good. Thanks. Okay, great. So we can, well, we have already online, so we're glad to today have our own Professor Wang Chu, who is a distinguished professor in Purdue ECE, to give today's PQC seminar. So Wang is a world-leading expert in wave physics, particularly computational electromagnetics. That's, I think, the area he worked on in his career. He got all his degrees at MIT and spent most of his academic career in University of Illinois. That at Purdue have people recruit one to Purdue, I think, a few years ago. And he is also quite active member of PQSEI. And in recent years, he has ventured into the using quantum world and with a lot of interesting ideas. And Wang is a member of the National Academy of Engineering. He served as president of IEEE, I think, WAVE, the Antenna and Propagation Society. For several years, he also served as a dean of the Hong Kong Engineering at Hong Kong University of Technology, one of the development in Asia. He has a substantial experience in the higher education, in addition to a distinguished career in engineering. It's all yours, Wang. Thank you very much for giving today's seminar.
Yeah, can you see my screen or?
Yes. If you could show a full screen, it will be a little bit better, but yes, we can see.
Okay, I put it full screen then. Can you still see them, my screen? Hello?
Yes, we are seeing the presentation mode on my screen, which means we can see your next slide as well. Sometimes you can change the display setting.
I think there's a way to do that. Let me remember to see if I know.
But it's fine if you cannot change to the normal.
There's a way to do that. Let me see if I can.
Yeah, go under display
There's
settings
a display
and swap.
setting.
This one to do it, right?
Swap.
Swap
Does it work
the first
now?
one. Try the first one.
Good.
Does it work now?
Yes, thank you very much.
Well, thank you everybody for coming to my seminar. And I hope this could be an interesting seminar that instill collaborations between different groups at Purdue as well. And thank you, Yong Chen and David, for inviting me to give this seminar. I have been following this PQSEI seminar series. We have learned a lot from them. I hope you can learn something from my profession as well. I gave this seminar in August, just recently, online, remotely, to a conference, ICCEM in Singapore. It was regretful that I could not travel there. I just gave it from my home. I actually like Singapore very much because I grew up in that part of the world. Peninsula Malaya is just about 150 miles from Singapore. So I gave a keynote talk there, and that talk was aimed primarily to electrical engineering, specializing in the field of computational electromagnetics. In other words, all those people are classicists. They know classical electromagnetics really well, but few of them know quantum theory well. So I had to make the talk so that it's understandable to those community of scholars there. And so I like to begin the talk by saying that knowledge grows like a tree. And our knowledge is rooted in the fundamental mathematics and sciences. And then engineering taps this knowledge and grow them first into science-based engineering. And from science-based engineering, we develop them into application-based engineering. And from that, the knowledge transpires to become real-world applications and technologies. And when I first came to Purdue, I was given the task of teaching a microelectronic course with Ji Hong Chen to second-year students or sophomore students at Purdue. And it was quite a challenge, in fact, to teach to sophomore undergraduate electrical engineering. And you really have to make things really simple. So simplicity rules, and you have to speak in very simple languages so that undergraduates can understand you. And because we transfer this knowledge and share them with undergraduate students, they, together with the rest of the engineers from the rest of the country in the world, perhaps can now put 60 billion transistors on the chip due to the compounding effect of nanotechnology and so on. You can see Moore's law being plotted over here. And I like to say that everybody in this tree is equally important. I wouldn't like to say that people who work down here are more important than people who work up there. It is like the proverbial story of the human body parts. You probably have heard about the story where the nose quarreled with the ears and the eyes and the mouth. And when one of them protested and didn't want to do the work, then the human being suffers, okay? So I personally prefer to do science-based engineering. That's why I'm quite interested in quantum technologies and so on. So what are the important milestones in quantum interpretation and quantum information? Well, in the early days, what they found was that if you can measure things really precisely down to the quantum level, quantum measurements are random. At the time, there were two prevailing schools of thought. One actually was promulgated by Einstein and his colleagues using the hidden variable interpretation of this randomness. According to Einstein, there is a hidden variable to every experiment. And the hidden variable is random, and hence the outcome of the experiment is random. However, there's another school of thought headed by Niels Bohr of Copenhagen. In that school of thought, it will say that one does not know what a quantum state is until you have done the measurement. Okay, so there were two competing schools of thoughts, and John Stuart Bell, who was actually a big fan of Einstein, a mathematician who came up with an inequality. And he says that if I come up with an experiment of two vectors, A, B, and C, and if I do expectation value or measurements due to those 2 or 3 variables, you can come up with this inequality, okay? If Einstein is correct in his interpretation, this will be smaller than that. And if the rest of the world is correct, or if the Copenhagen School of Interpretation is correct, then the equality would fail, okay? Then in 1982, and maybe even some scientists before that, Alain Aspect of France, did some quantum optics experiment, but he showed that this inequality is always violated, okay, which means that Einstein's School of Interpretation was not the correct one. Niels Bohr's School of Interpretation is the correct one. Actually, I find this to be a very beautiful theorem, a very beautiful milestone in quantum interpretation and quantum information. It says that our karma is not written on our forehead when we are born. Our future is in our own hands. This is actually a very uplifting epiphany of the world, if you understand what this means. So, well, what is so strange about quantum theory and quantum mechanics and so on? What it says is that if you have a state, a quantum state, the quantum state is a linear superposition of many states. This is, in fact, the core of quantum weirdness. Okay, for instance, a ghost can be anywhere in space. If you have a person in the room, that person can be anywhere in the room, and only ghosts and angels can do that. Here I have a comic picture of a ghost hopping around in the room and an angel been having apparition where you don't really know where the angel is, okay? But this kind of phenomenon can happen in the quantum world, even though it's very hard to see this in the classical world. if we can exploit this weirdness in the quantum world, we can perhaps develop new technologies. Okay, so the principle of linear superposition promulgated by the Niels Bohr's School of Interpretation has come up with very ridiculous stories, one of which is the story of Schrödinger live cat versus the dead cat. So I have a big cat, which is a Siberian tiger on the left. And then I have a dead cat, which presumably was a Malaysian tiger, a Singaporean Peninsula Malaya tiger, because of the period it was taken. It was killed by perhaps an Englishman, I don't know. He has a mustache, so he might be a Frenchman, I don't really know. So this become a ridiculous story, and you probably have read about this story before, Schrödinger's cat, and they even sang this in the Broadway movie, I believe. So what is so unusual about this linear superposition of states, which means that if you can design a quantum computer, a processor with 53 qubits. Qubits is a quantum bit, and you can have 2 to the 53 possible states. Okay, and if all these qubits are in quantum coherence, you can have this quantum computer be in the linear superposition of 10 to the 16 states. And they were like angels and ghosts dancing on this qubit. And if you can choreograph an algorithm to get these angels and ghosts to work for you, they can do wonders. They can make things a lot faster. That's why quantum computer is so appealing. So let me talk about quantum coherence made simple. In quantum theory, it says that you have to describe a quantum state or wave function. Okay, and that the probability of being in that state at a certain position and time is given by the square of that wave function amplitude. And so if I have a quantum state, which is the linear superposition of 2 states, you can very easily go through the mathematics if these are all complex numbers, because quantum states can be complex. When you solve Schrödinger equation, you will have square of this function is the square of the first function, the amplitude square of the second function. If the first function represents a dead cat, the second function represents the state of a live cat, then you have an interference term between the first function and the second function. Okay, this interference term actually means that the cat is neither dead nor alive. Usually in the classical world, this term averages to 0. This is not a nuisance to us in the classical world. But in the quantum world, you can have this term work for you, and they don't necessarily average to 0. And so the key is how to engineer a quantum system where this does not average to 0, whereas you will not see the ridiculous notion of a dead cat and a live cat simultaneously occurring. And this is the meaning of the third term here, where the cat is neither dead nor alive, but we don't see this in the classical world. So let's talk about spin states then. Spins, if you open a simple textbook in quantum mechanics, you say that the state of a spin is written as a linear superposition of the up spin and the down spin. And then the coefficient of linear superposition can be written in terms of what we call the position or the direction of the spin in the Bloch sphere. This spin is now making an angle theta with the z-axis and the angle phi with the x-axis. And you can write the superposition of state in this manner. And for simplicity, we can pick theta to be pi over 2, and we come up with this rather simple linear superposition of 2 states. So a classical bit will be something you have on the left-hand side, whereas the right-hand side is a quantum qubit, quantum bit, which is a linear superposition of 2 bits, one in the up state and one in the down state. Okay, so these quantum states, they evolve according to this equation, which is often attributed to Schrödinger, even though when he first wrote it down, he used this only for the hydrogen atom. And even later on, when Dirac wrote the down his direct equation, you can still time evolve the state of a direct equation using this equation. I would rather call this the quantum state equation, because if you write down Maxwell's equations, the Hamiltonian also evolve according to this equation. So if you time evolve this thing, it's very easy to solve if this is a constant. The formal solution to this is that, and this is a unitary operator and transform. And I would say that this is actually very similar to the state variable approach in control theory. I bring control theory up because this is one of the hot topic or interesting topic for an electrical engineer, because as an electrical engineer, almost everybody has to take a course in control theory. And there you describe the state of a system with a vector V, and maybe describe the system with a control function H, and then you can easily solve the time evolution of the state of a control system, describing how a time evolves. I think this control people took the idea from the quantum people, okay? Because if you look at the historical timeline of when this thing was used in control theory, it was much later after the development of quantum theory. But because control theory is easy to understand, maybe we could use that to inspire and let us know how quantum theory really works. Say if you want to describe the state of two factories concurrently, factory 1 is described with a vector, state vector of V1, and factory 2 is described with a state vector of V2. Then the aggregate state of the two factories together is just a product of the two states. And mathematically, you would like to write this as an outer product. Okay, this is the aggregate state vector. And usually physicists are quite sloppy. They just write an outer product in this manner. And it actually mathematically means that. So we can do likewise to expand the quantum state of 2 qubits. For instance, we talk about the quantum state of 1 qubit. And when we have 2 qubits, the quantum state will be just a product of the two quantum states. The psi represent the state on the left, psi prime represent the state on the right, and very sloppily, you can write it in this manner. So what you do then is to take the quantum state of the one on the left and then multiply with that of the quantum state on the right. And if you expand that out, you have 4 terms, okay? And interestingly enough, you can label these quantum states using a binary mathematics. This is called 000110111 state. And you get the linear superposition of 4 states. So you can extend this idea for n registered qubits. And say if you have 3 qubits, 2 to the 3 is 8. Okay, you have 8 possible states, and if you expand the product out, you have 8 terms. And interestingly enough, you can actually label this using decimal number as well, because if you translate this to decimal, it also goes from 0 to 7. So we have 2 to the 53 states, or 10 to the 16 states, if n is 53, and that is a humongous prowess available to us in a quantum computer. Only if you know how to choreograph the states to dance constructively for us. So I like to show the power of quantum parallelism using a very simple example, quantum Fourier transform. I took this idea from reading Nielsen and Chuang's book, but I translated it into terms I hope is very easy to understand for everybody. Okay, so as I said before, each qubit is represented by a quantum state as such, and if I have many of these qubits, n of them, then the total quantum state that we have in the system is a product of all this state of individual qubits. Moreover, if we have a system where we can control the phase, the phi of each qubit individually by probing or exciting it with an EM signal, then I can get phi 1, phi 2, phi 3, and phi n to be all different in these qubits. And when I multiply them out together, okay, I will have a linear superposition of n, which is 2 to the power of little n, quantum states. And if I choose my phases judiciously, when I apply this EM signal, this EM signal is actually quite well known, is in NMR. They are called pi over 2 pulses or pi pulses and that kind of thing. There's quite a bit of knowledge on how to manipulate spins in NMR. Okay, so if I choose this thing judiciously, I can have this could be converted into a Fourier series transform. And if I have a quantum state that has this factor in it, then I can extract this Fourier transform, and it only takes order n square operation to perform this Fourier transform. If you translate n to capital N is proportional to log square n. And all electrical engineers know that our present state of affair for performing a fast Fourier transform has a computational complexity of n log n. So even if you know how to program a quantum computer to do quantum Fourier transform for you, you can have tremendous speed up for you, especially when n is very, very large. And this is important for Shor algorithm. Of course, together with Shor's algorithm, you have to do order finding and period finding as well. So how can CEM help? CEM here stands for computational electromagnetics. And if you look around and listen to seminars, the problem we have now, the present day quantum computers are very noisy. I attribute that we do not have enough knowledge base in this area. It takes about 70 years for us to grow from a vacuum tube computer to a computer that you can put inside your cell phone. So we are still in the very formative year of quantum computing, I believe. And spins are mimicked with two-level atoms or artificial atoms or real atoms. You can see different kinds of competing ideas out there. And many of the spin dynamics of the two-level system are done with probing or exciting the system with the electromagnetic field. So if you can do better math and physics modeling with computational electromagnetics, we can help to reduce errors and noise and help to improve precision engineering. In order to get these qubits to be dancing in unison with respect to each other, I believe quite a bit of precision engineering has to be done. So what did we do in our group? We recently derived a set of Maxwell's equations that we call the quantum Maxwell's equations. They actually are in the Heisenberg picture. They are derived using energy conservation. And also we quantize this in the coordinate space. Most of the textbooks, if you open up any physics textbooks, they will usually quantize this in the momentum space or Fourier space. And if a system is nonlinear, you cannot even take the Fourier transform of the system to quantize it. So our quantization process lends itself easily to a nonlinear system. I think one of my students has even applied this to a nonlinear system. In addition to solving the quantum Maxwell's equations, a new player comes into play because we have to solve the quantum state equation to track the time evolution of the quantum state. This is not needed in a classical system, but I believe that this is needed in a quantum system. So here is just an example of what happens in the quantum world. Whatever that is a variable that is measurable in a classical world becomes a random variable, as known to physicists long ago, that whenever you perform a measurement, the measurement has a mean and a standard deviation, okay? And an optical measurement of a high-speed pulse might look like this in an optics lab with a lot of noisy data. And this data has a mean that you find by using this formula, and you can find its variance, and you can find even its nth moment of this random variable. So what did we do? Well, we have to solve Maxwell's equations, and in order to solve quantum Maxwell's equations, we translate it to solving a very simple wave equations, because a wave equation is derivable from Maxwell's equation, and we solve it by mode decomposition. Say if you have to solve this wave equation of a complicated form where epsilon and chi are arbitrary, one way to solve this equation is to use mode decomposition or separation of variables. You assume that phi, the time variation and the space variations are separate. You can easily show that this time variation satisfies this equation. whereas the space variation satisfies this other equation. And this equations, of course, has no closed form. You have to actually solve it numerically. And we in the CEM community are quite good at this, how to find numerical solutions to a complicated PDE, such as this one. Okay, you can easily show that if you have a Hamiltonian of the system, the Hamiltonian is dependent on something like this. And if you go to the math, after you have performed mode decomposition, you can show that the Hamiltonian essentially is the sum of the Hamiltonian of individual modes. Okay, this is the kth mode in the system, and this is the kinetic energy of the kth mode, and this is the potential energy of the kth mode. Okay, and then with this mode decomposition, you can easily connect to the quantum world because these modes are oscillating like a classical pendulum. And you can also quantize a classical pendulum to become a quantum pendulum. And if you know how to make the connection of connecting these classical variables to the quantum lowering and raising operator, you can easily convert this Hamiltonian into a quantum Hamiltonian. And any field variables that you have can also be connected to this annihilation and creation operator. And hence you have a quantum version of a field. And a large part of this is still very classical, except for having this operator tagged to it. So I have a very gifted postdoc. His name is Dong-Yap Na. He's a very gifted genius in many ways. Before joining my group, he knew nothing about quantum theory. And very quickly, he picked up this knowledge and was able to do quantum research with me. And the first thing we did was studying the beam splitting using computational electromagnetics, where classically you have this scenario, but by solving quantum Maxwell's equations, quantum weirdness comes about. You can use linear superposition of quantum states and so on. You can complicate things like this, the G2 correlation, and replicate the Hom-O-Mandel effect, which has been known since the 1980s, I believe. Okay, we can show that the two photons either bunch up to go one way or they bunch up to go the other way. So when that happens, it's entirely a quantum effect. Then the correlation between these two quantum states is zero. That's where you have this dip in correlation function if you were to seek the G2 correlations between these photons. Okay, and then Dr. Na also developed this quantum FDTD for solving quantum Maxwell's equations. We choose FDTD because FDTD has become a very popular algorithm for solving Maxwell's equation. FDTD here stands for finite difference time domain. If you look around the country or the world, almost every physics lab has the homegrown FDTD code because it's so simple to write. So the idea is rather simple. So if you have a quantum Maxwell's equations that I have written in the simplest form, if you would discretize the space and time, you can convert this equation into a set of finite difference equation, but it's still not there yet because A hat is an operator. And operator here is an infinite dimensional operator, and it's too much a burden to carry this around in FDTD code. So Dong-Yap Na came up with the idea of connecting this infinite dimensional operator to an annihilation operator that is localized in space and connecting what we call the vector potential hopping function, which is a scalar number. And if you plug this relationship into that, and then this quantum part will factor out, and this other part is entirely scalar, then one needs only to do FDTD on this scalar part of the algorithm, and you can get quantum effects out of that because the quantum effects is still buried in this annihilation operator over here. So Dong-Yap did some experiment to see if we do truly capture quantum effects and the weirdness of quantum effects to see if we can reproduce the Hom-O-Mandel effect again. And here with quantum FDTD, he was able to, for instance, study the correlations of the photons on two ports of the beam splitter and show that there is in fact a dip in the correlation function if you do it correctly, which means that we have captured the classical well as a quantum physics of a photon using our simulation procedure to solve quantum Maxwell's equations. And I don't believe that this has been done before. Well, recently we did one more thing, which is actually to model dispersion. And if everybody just look at classical Maxwell's equations, like if you look at QED was preoccupied with solving Maxwell's equation in vacuum. So there's no dispersions at all. But if you do quantum optics, working with fibers and many of the optical components, you will have dispersion effect. And how do we model that? That is a part of a material property. So we start by coupling a field system to Lorentz oscillator, which you can describe by this system. And P dot here, which is a time derivative, is VV, is just a time derivative of that. You can find another Hamiltonian, which is similar to that, where you have conjugate variables, okay, pi A, P, and A, pi phi and phi, and write down a Hamiltonian. And if you do energy conservation, you can show that these equations pop back out at you, which is the classical equations of motion. These are Maxwell's equations written in dimensionless unit, but the difference is that we have the equations of motion for the Lorentz oscillator in these equations as well. So having done that, build a bridge between the Hamiltonian mechanics and classical Maxwell's equation, we can elevate ourselves to the quantum world quite easily. So I won't go into the detail, but the simple rule of thumb is to replace all operators, all field variables with operators. And if you do that, and again, if you go through the energy conservation argument, you can derive the quantum equations of motion for these variables. These are now quantum field operators in the Heisenberg picture, and these are the quantum equations of motion. And Dong Yap has again done that for the first time. I don't believe anybody has done this before in the history of modeling quantum system with Maxwellian effect. And we are able to actually put in Lorentz oscillator in the medium, model them, and then show that if you have a beam splitter, the dip will be affected by your presence of a Lorentz oscillator due to dispersion. Okay. Another thing that is very interesting to us is quantum sensing. It has been talked about by using entangled pair of photons, and one of the photons you keep to yourself, but the other photon you send to the target. And then by using the entanglement of this photon, you can greatly increase the sensitivity of your measurement system. You can actually detect the signal from this target even in a more noisy environment. And I noticed that Andy Weiner's group does work like this. He studies time frequency entanglement. He passed his photon through a ring resonator and get the comb out, and then he gets different kinds of entangled photons out from his lab. And then you can even get higher dimensional entanglement. I'll let you talk to Andy Weiner to figure out the physics and the detail of this. And what we show is that if you have a d-dimensional entanglement, I take this slide from one of the talks given by Dr. Dong Yap Na in a research group, you can enhance the sensitivity of your system by this. Either is like the reflectivity from the target, N is the background noise. You can lift your measurement system out of the noisy background if you have this kind of thing. And also that the number of trials to detect the presence of a target is reduced by D. If you have a d-dimensional entanglement, you have to take a lot less measurements to detect the target. This can be very interesting for quantum radar as well as quantum biosensing, if we apply this to biosensing as well. So Dong Yap did some computer experiments because we have the facilities to do computer experiments now. We imagine a signal coming out of a 3-level system with a signal photon going that way, and then a ideal photon going that way. And then we coincidence count, and he could generate this syntactically using syntactic data using computer codes. Okay, because we believe that our modeling is full physics, and then if you can generate frequency combs such as this one, you can get you can do all kinds of interesting experiments on a computer. Of course, the real test of the pudding is still a laboratory experiment. And we also can do ghost imaging experiment. These are again in synthetic experiment where you set up a ghost imaging experiment in a computer and study the G2 correlation between the photon traveling to the left and photon traveling to the right. And when a hole emerges, okay, this photon doesn't come back, and then you have zero correlation between these two detection systems. And you can use that to actually image this system with this detector not having to detect any photons coming out from the system, okay? And I have another student, Dr. Thomas Roth. He, again, is a genius of his kind. He's actually very gifted. He did this part of his thesis only in the last 6 months. I was amazed at how fast he did this. And he used his knowledge of computational electromagnetics to study a single photon source. The single photon source, he got it out of some of the groups of Devoré and so on. So there are some details which I will not talk about. There is a small Cooper pair box here, Qubit. A Cooper pair box perhaps is a superconducting Cooper pair box that generates a photon. And then the photon goes through the system, and then it might travel to the system and then come out to the thing. And what has been done in the past is that this has been done using circuit QED. And what Tom did for the first time is to input propagation effects, that he can actually model the retardation of the microwave photon going from here to there. Perhaps that's not important for this system because these systems are engineered so that circuit QED is important. Wave propagation is not important, but with its simulation capability, we can make a system where maybe when the microwave photon has a much higher frequency and retardation effect is important, but Tom's work will become very important. What he did was that he actually has an input here. I believe this is where the Cooper pair box was. And then he was able to model the interaction between the field. He used a field approach to model the interaction between the field and the qubit. Not the qubit, sorry. It is a transmon. The proper word for it is a transmon, okay? The Devoré's group called this a transmon. And he can solve the equations of motion due to this coupling. And in order to simplify the system, to linearize it, he threw out the field atom coupling term so that he can concentrate his effort on just studying the atom. The atom here is actually the transmon, artificial atom. He worked with the Lindblad master equation to study the time evolution of the transmon, and he assumes weak coupling so that there's no back action of the field back to the transmon. And if there's strong coupling, you will see this kind of Rabi type oscillation going on. But if there's no back coupling, you will have this kind of simple things going on. And Tom, he was able to do this modeling. And when I saw this picture, I said, Tom, where did you get these pictures from? Did you get the permission of the author to use them? Tom told me he drew them himself. Okay, I was taken aback. I was flabbergasted because it takes a lot of pain and patience to draw this picture. And Tom just drew this picture all by himself. Okay, he doesn't have to get the permission of the author. And he also meshed up this geometry using something that I think he did all on his own. You can see that the meshes are very fine in certain places, and the meshes are quite coarse. And this is what we call in computational electromagnetics, a multi-scale geometry. Okay, and Tom was able to use computational EM to calculate the spontaneous emission rate, we are using the Green's function, and then plug this back into the Lindblad-Masters equation, and then solve the system concurrently. So this is his spontaneous emission rate calculation using full-scale computational EM. And then later on, it was able to show the effect of propagation, photon propagation, as a photon propagate from one end of the transmon to the other end. But this might not be a big effect, but it could be an important effect when retardation effect becomes important. Okay. And the last bit of my talk, I'd like to talk about another activity that we have been doing in our research group, which is to calculate Casimir force. Casimir force is the attractive force between two objects. Here we illustrated with two very simple parallel plates. And when you have two simple parallel plates, then there will be electromagnetic modes set up between these two parallel plates. Okay, and the electromagnetic modes classically says that if there's no photon, there's no modes, there's no field. But in the quantum world, apparently, if you just study electromagnetic oscillation quantum mechanically, there is a ground state which corresponds to no photon or no field, but yet it has no zero energy. This is called the 0-point energy. It's the lowest state of the quantum harmonic oscillator. I took this out of Wikipedia. This is a classical oscillator. These are the wave functions describing the quantum harmonic oscillators. And they have all these different states, okay? And there's this 0-point energy that is there, even if you cool the universe down to 0 temperature. That is, if you get all oscillators of the world to be cooled to the ground state, this is still there. And this mode will account for the attractive force between two parallel plates. I believe that if this force is not there, the universe will fall apart if you cool the world down to 0 temperature. And it's this vacuum fluctuation that is holding the universe together. So how do we find these modes? Okay, so that was just an illustration of a very simple parallel plate waveguide. You can find the modes on papers using pencils and papers calculation, but in general, if you have a very complicated structure such as this one, finding the modes is not easy. And I just use circuit theory as an illustration. If I have a complicated circuit like this, how do I find the modes? And you can set up the circuit theory problem with an impedance matrix Z times I being the currents on the branches, V being the voltage on the nodes. And one way to find the resonant modes of the system is by setting the driving voltage to 0 and then set the determinant of this to be 0. And that will give you the resonant modes of the system. You can set up a similar system in electromagnetics calculation, even though it's more complicated than circuit theory. You can set up electromagnetic theory in such a manner, and you end up with an equation that looks like that of circuit theory. Okay, this J are the currents on each of these facets. And then again, to find the resonance of modes of the system, you set the determinant to 0 and then find the resonant modes. These resonant modes are important because they are there to account for the 0-point energy and the vacuum fluctuation of the system. So even though if you switch everything off, the vacuum fluctuation is there. And in order to calculate, there's a host of CEM methods available. Okay, and I did this with my students, mainly during the time when I was at the University of Illinois. You can show that you can use a Cauchy integration technique and show that the Casimir energy of the system is proportional to setting these determinants to 0. This is reminiscent of the fact that we have to look for the resonant modes of the system. That's why we set determinant of Z to 0. And then if you apply Cauchy's theorem, we call this the argument principle. You can actually extract the mode of the system by doing a contour integration rather than having to search for the individual poles of the system. Okay, and Z is just the method of moments method, the moments matrix. And I have a student who did this for highly complex structure. He was able to do this for interdigital structures such as, there's the interesting thing is that he found both attractive force as well as repulsive force. The Casimir force has been an interesting force to people who work in MEMS, micro electromechanical systems, because in order to engineer a MEMS system, you have to have the presence of both attractive and repulsive force. So if you can engineer a system where both repulsive and attractive force exists, maybe you can design interesting MEMS structures. Okay, he found that, well, by engineering such a system, you can have both attractive as well as repulsive forces, and maybe that can give rise to some interesting MEMS design in the future. And also talk with Shalev and Shasha of Berk's lab in university. And when I look at the quantum optics lab, I have visited some of the optics like that of Tong Chang Lee of physics department and so on. And they are humongous in size in terms of wavelengths. Okay, they're humongous. All the components are huge. Even if you look at ring resonators, they are huge in size. Okay, so what I found in microwave engineering is that you can derive and design couplers that are on the order of a quarter wavelength. This coupler is on the order of a quarter wavelength. This is called a branch coupler. This is directional coupler. And always amuses me as to what is the reason between the huge difference in size. I thought maybe the secret lies in quantum plasmonics, because when you have a plasmonic mode on the waveguide or a structure, that mode is highly confined. All the waveguide modes in microwave are highly confined because we use metal strips to confine the modes, whereas the waveguides in optics are made with dielectric waveguides. They are not highly confined, okay? So because of the tight confinement we have in microwave, we can design structures a lot smaller. Can we use this idea to design structures with highly confined modes? I remember that back in the 1980s, there were some talks about making optical computers to replace electronic computers. The reason why it failed was because Alan Huang was one of the names that came about. He was at Bell Labs. He was giving speeches around the world. And if you look at his optical computer components, they're humongous like this, okay? They take the whole of the optical table to design. So before you can talk about optical computers, you have to talk about miniaturization. How can we make these computers much smaller? So maybe nanoplasmonics is the key to this. If you can work with nanoplasmonics, where the modes are tightly confined, we can perhaps make optical components that are a lot smaller. So in conclusion, I'd like to say that I give an introduction on quantum parallelism and show its prowess by using a very simple-minded approach, interpreted my way. I don't think you can find this in any textbooks. Okay, I use quantum Fourier transform as an illustration. And a quantum computer has high payoff, but engineering a good quantum computer is still very difficult. And we have developed a CEM method, computational electromagnetics method, to solve quantum Maxwell's equations. These quantum Maxwell's equations are based on our own formulation, not any that you can find in the textbook. We can solve that using mode decomposition as well as quantum FDTD. This has been the work of my genius postdoc, Tong Yap Na. And then recently, my PhD student, Thomas Roth, has combined Transmon in circuit QED and put in his share of time domain integral equation solver from computational electromagnetics to solve this problem. Okay, I just report on some recent progress we did on Casimir force using computational electromagnetics. So I believe that better math and full physics is very important. Okay, we have to be able to capture dispersion. We have to be able to capture quantum weirdness. We have to be able to capture the principle of linear superposition in quantum theory. And if you can do this through CEM, it can help improve the design of quantum computers. Okay, and I always tell my students, if your mathematical logic is good and if your computer's code is good, they don't tell lies. If you can cheat on any of them, your thing will fall apart. Okay, and it's important for us to find the simplest approach to explain things in order for knowledge transfer between disciplines in the development of advanced technology. And then the issue of 7 transistors on a chip is an illustration of that. Okay, I'd like to thank all my colleagues at Purdue for interesting discussions and support. And I'd like to show this picture to the audience when I gave this talk internationally as to how beautiful Purdue is. Okay, and of course, Armstrong is there always. And these are members of my group and people I collaborate with. Okay, I collaborate with a lot of people. I don't have a lot of research fundings, but I do talk to a lot of people around the world. And these are some of the papers that we have published that are related to quantum technologies. Okay, that's the end of my talk. Thank you for listening. I entertain any questions that you might.
Well, thank you. Yes, we do have time. So now, welcome questions from the attendees.
Either I swam you with too much.
Maybe I can start with a very.
Okay. Okay, good. At least I have a question. I thought maybe I swam.
Can you give a little bit? Maybe I start with this very general. Can you give a little kind of a maybe perspective? I think I asked this question a while ago. This what you call quantum Maxwell equation. Of course, Maxwell equation has been around a long time, and quantum electrodynamics has been around a long time. What are the kind of other attempts or your approach kind of leading to what you now call this approach of quantum Maxwell equation?
Well, this is a new area to me, and I go through many textbooks and even talk to Chris Green of the physics department as to how people do it in the quantum physics community. Of course, I'm familiar with books by Tanuji and even Mendel and Wolf, and also many physics books that does this. Invariably, most of them would just quantize Maxwell's equation in the momentum space. And in the momentum space, I mean that they take Fourier transform of the classical Maxwell's equations, convert them into Fourier modes, and then connect those Fourier modes to a pendulum, and then quantize those modes. But what we have done here is actually to have quantized Maxwell's equation without having to take a Fourier transform. And because we don't have to take Fourier transform, I think that's why we can do things like what Tom Roth did. He was able to incorporate a nonlinear system and write the Hamiltonian down for a linear system connected to a nonlinear system, because if we have a transmon, essentially it is a nonlinear system. So this can open up avenue to new investigation. I just feel that there's not enough knowledge base in this area. Okay, that if we work on it, and if more people work on it, we can develop the knowledge base needed to support technology advancement in this area. Okay, I think I say that somewhere. Not enough knowledge base. And when I talk about this not enough knowledge base, people would tell me, isn't QED been around since the 1920s? Well, it's true that Dirac and Tomonaga and all those people started QED, but those were just interested in interaction of photons in vacuum. But what we are interested in is quantum optics, where the photon is actually going through a fiber, through a very complicated geometry, even through all kinds of plasmonic media. That kind of quantum Maxwell's equations have not been solved. Neither any of the QED people before us have done that. And if you feel that I'm wrong, please point that out to me, because I did go through lots of literature research and couldn't find anything out there. So I say that there's not enough knowledge base in this area.
I have a question. So this is Yulia Pushkar from physics.
Okay.
So this is a very general question. So you were talking about using photons for detection, like quantum sensing.
Yes.
Your quantum radar, very interesting. I like to keep my photon in the pocket.
Okay.
So how long the coherence survives? What is the current limitation? Imagine we have this radar. So the photon in my pocket will remain coherent for how long?
Well, I think coherence is not the key issue here, is entanglement. I have read in a newspaper, okay, I don't have first-hand experience. They have sent 2 photons that are entangled around Geneva or some big cities like in Europe on the optical fiber. And they test entanglement of the 2 photons. Even after traveling many kilometers, the 2 photons are still entangled. And if you study entanglement, it's quite a different issue from coherence. Coherence is what you need in building a quantum computer. Entanglement is there, even though the 2 photons fly apart. Okay, if these 2 photons fly apart. Okay, each go its own way. And according to what I read in the news, they have made these 2 photons flown apart through kilometers of optical fibers in Geneva or something. Correct me if I'm wrong. Many of you might have remembered this story much better than I did.
Yeah, this is very interesting. But like if it goes through the atmosphere and can kind of scatter randomly, it's still, that's the same as going through this optical fiber.
Ну что ты, елки-палки, я же не вижу.
I don't understand Russian, Vladimir. Anyhow, I would imagine that would be one of the research directions that we should have, which is that, these photons are going to fly through the atmosphere. You'll be scattering by the atmosphere. Would that cause the entanglement information to be lost? Okay, so they have done that on optical fiber. They actually even have done that in China using satellite communication, where the photon is mainly traveling through the outer space, which is vacuum. There's very little scattering loss there. So they have record-breaking teleportation experiment where a photon flies through kilometers, essentially through vacuum. I would imagine that if this environment is very, very turbulent, like a cloud-covered environment, you will lose some of the quantum information. You will lose quantum information. But I don't know if you lost entanglement. Okay, correct me if I'm wrong. I just feel that entanglement is always there, but quantum information gets distributed to other places as the photon travels.
So when, since everybody heard me anyway, I'm visiting a dentist with my daughter. And I just like to say that I'm very much impressed with the machinery you developed. That certainly was kind of missing. And I think it looks like it's a very powerful tool to play with. And I applaud to work you and your group did. We certainly would be very much interested in collaborating on this and taking it to nanoscale with plasmonic or whatever. But very, very impressive. Thank you. I find it as a fantastic talk. And most importantly, you really seem to develop good machinery to describe this phenomena, which was largely missing. Thank you.
Yeah, thank you for the compliment. I also feel that I used to do experiments many years ago. I have stopped doing experiments because they cost a lot of money. I know that Berkeley Nanotechnology Center has wonderful experimental facilities. I like to collaborate with researchers there if possible, or any other scientists and researchers around Purdue who have good laboratory facilities, because doing computer modeling is not the whole thing. I always tell my students, the real test of the pudding is experiment. You can write down all kinds of beautiful theory on paper, and if the theory is not tested with experiments, the theory is still useless. Okay, so I would very much like to collaborate with environmentalists if I have a chance.
Other questions?
Yes, or no question. Then either my talk is
Well,
too bad. It swamps.
I have another question. One, sorry, and
Yeah.
maybe also a comment. I like maybe it's a little follow up what I was saying. I think I mean I appreciate this effort, kind of looking at light matter interaction. You know, of course, the quantum into the quantum region, but more in the more complex media, right? That's much along the spirit. And also one thing it's I'm very curious is, you know, I'm impressed by I think there's a lot of techniques, also the machinery that people in, let me roughly speak, classical electromagnetism and also the traditional optics developed. That's very impressive. I like the question you posed that apply techniques from area like CEM to today's quantum technology. For example, one area research where I don't know that much, but I'm very impressed by, for example, using computation ability to overcome the experimental limit. For example, in the old days, we tried to improve the hardware to improve the resolution of imaging, right? I'm very, interested in development in several years in the past that people trying to, for example, using more complex light source or random light source and utilize the computation technique to actually improve the optical imaging rather than just improve the hardware. So I see an analog here. So today we are kind of saying these noisy quantum computer, of course there are a lot of physical limitations, decoherence and all that. But you point out correctly that it's also, we're dealing with a complex environment. For example, in this superconducting resonator, circular QED, all this platform with the light matter interaction. So I wonder if you thought about maybe by harnessing these advanced computation technique, designing microwave waveforms in this architecture that overcome some of the limitation of the hardware that can improve the quantum operator in these noisy, say, superconductor circuit QED quantum chips, for example, the Google quantum computer just showed. Sorry, this is a long question, but it's kind of motivated by what you're saying in this.
Yeah, I think that's a very good question. Of course, one of the areas that has attracted the interest is super resolution in optics, and right. you can justify super resolution in optics very easily on paper, just like what John Pendry and his cohorts have done. But the real test of the pudding is still experiment, because when you look at some of this super resolution theory, they rely on the measurement of evanescent waves, which essentially has dropped to the noise floor of the measurement system. And if you design measurement systems where the information has been buried by the noise floor, then it's a useless attempt, in my opinion. You have to work with experimentalists to understand what is measurable, what is not measurable. And that part only an experimentalist has a good feel. As a theorist, we can compute everything to 12 decimal places, machine precisions very easily in a computer, but it has no meaning. Okay, it has no meaning until you check with the measurement capability of a laboratory. So I think people should talk. There should be cross-pollinations both ways as to what is possible in terms of measurement and what is possible in terms of modeling. And we shouldn't let one go too much the other way, okay, so that there should be a reality check. And I think theories should be anchored to the floor with experimental data. Otherwise, we will be like a kite without a string. We will just fly around and not having a direction. Okay, so that's my feeling.
Hello.
Oh, sorry. Yeah, go ahead.
Okay, so I have one generic question. I'm wondering what is the fundamental assumption you're making when you're deriving quantum finite difference time domain solver? I'm meaning how generic your solver is. Because, for example, when you're representing the amplitude operator, right, this like hoping Hamiltonian product with a annihilation operator, right? I'm wondering what kind of physical meaning you like trying to introduce to the framework here.
To say it correctly, to say like a mathematician, classical Maxwell's equations has been around for many, many years, 150 years at least. And most of the time, we assume these equations to be an axiom. So we take an axiomatic approach in designing a computational algorithm. We take Maxwell's equations to be the ultimate truth, and then design algorithms to solve them. Here we are taking a similar approach. We have these Maxwell's equations that have been derived, I hope logically and rigorously, okay, using our process of quantization. So we are taking this as an axiomatic starting point. And from this axiomatic starting point, we can design all kinds of algorithms to solve them. And here is just a Maxwell's equations in its simplest form, but this is not an ordinary scalar number, but a quantum operator. And if you discretize this in a naive fashion, you have this big burden of carrying this around yourself. But if you find a relationship, as Dong-Yap Na has found, between this field operator and the local annihilation operator, you can show very rigorously, okay, there's no logical flaw in going from here to here. Very logically, you show that this is the only thing that you need to finite difference, doing time stepping. So the axiom is this: assume this to be the ultimate truth. Going from here to here, there's no logical flaw as far as we are concerned. And that has been the kind of philosophy driving computational electromagnetics for many decades. That's why we can come up with high precision electromagnetic simulation tools and algorithm.
Yeah, but my feeling that when you are trying to introduce a quantum effect, right, into the Maxwell equation, you should kind of inevitably like introduce non-locality to the like fields, right? So even though, I mean, there should be some non-local effects, right? Probably.
Non-local effect. These are operators. They operate on the quantum state. The quantum state is non-local. The quantum state, no position dependence in it. It's just the state of the entire system. Okay. So if you have any quantum weirdness that comes about, the weirdness is manifesting itself through this quantum state. And these are operators. I can send you a paper on a derivation if you're interested. These operators have to operate on the quantum state and the non-locality and this entanglement effects and all this quantum weirdness that we have shown in the beam splitter comes about because of this quantum state.
Okay, I will check paper. Thank you very much for your answer. Thank you.
Okay.
I just wanted to briefly mention, because like those days we don't meet that much either in the department or another form. So potentially I'm very interested in quantum sensing for biological systems. Yeah, again, it's very turbid media, it's water, it's some biological molecules. So it would be curious for me if anyone at Purdue is working in this direction, and maybe we can discuss more.
Yeah, I think quantum sensing is a very nice area to go into, especially for biological sensing. You can improve the sensitivity of the system. You have to use very low energy level, because if you use high energy level, you have many photons, the quantum effects is not there. So you almost have to do very low number of photon measurements to see the quantum effects. And if you can use quantum entanglement to improve the sensitivity and the resolution. Again, I find that the knowledge base is very, very thin. For instance, I was guest editing a column on quantum technologies. I was trying to look for people to write articles on quantum radar. There are only a handful around this world who are working on quantum radar. and maybe even less on quantum sensing. So if there could be a group of people in Purdue who can work on quantum sensing, especially for biological sensing, that would be wonderful, I thought.
So, Yulia, this is a quick comment, and this may be interesting to some people in the audience. There is a program, some kind of expert program supported by the engineering faculty conversation group on nanoquantum, on quantum photonics and biology. I think this is Hongtang Li and Verheet, I think Mohit and Yongqing and Huang, 4 people. They have some, I think they've been working on this for more than a year. I think maybe you can talk to one of them and other people.
If there are any like mailing lists for different subgroups, probably would be great to somehow get connected.
Yeah, I think Yong Chen would be the
Maybe
right person
we
to
can
ask,
look into
since
this.
Yeah, he's running a center. He's one of the directors of PQSEI. He should know a lot of groups around our campus. Maybe you can help us build bridges between different groups.
Yulia, you're welcome to, we can add you to the PQSEI list. Okay, thank you so much, Wen, and thank you, everybody.
Okay, thank you. I hope it's useful. Okay, thank you for coming.
I'm sure we generate more discussions. We'll look for it. Thank you.